Okay, any questions so far? Go play with your toys. Go. Okay, so let's go ahead and take a look at these further. Oh, yes. Whoops, did I just like destroy it? Oh, I see. Okay, cool. Okay, so we saw that NH ammonium looked like this. Cool. So we have ways of talking about molecules like this. Alrighty, and so we can see that... What are we ignoring? Okay, whatever. If we look at this, we're going to describe this as a molecule that follows the AX4 type, where A is the number... Calvin, go away. You already got your treat. Central atoms. And X is the number of atoms bonded to central atom. Okay, so we see that AX4 means we have one central atom and 4 outer atoms. So we can see we have one central atom, 1, 2, 3, 4 outer atoms, and therefore this will be AX4. Okay? Is that okay? Don't see any questions coming up, so cool, great. So if we look at SO3, if we look at our central atom, how many central atoms do we have? We have 1, of course. How many outer atoms do we have? 3. And we also have a lone pair. Okay, so we have this now. E is going to refer to the number of lone pairs on central atom. Okay, so we have, in this case, AX3E. Alrighty, looking at water. Here, look, I'll do it like you guys do it. Boom. On our central atom, we have, of course, one central atom. We have 2 outer atoms, and we have 2 lone pairs. We can classify water as having the AX2E2 structure. Okay, is that all right so far? For this, we're only going to have one central atom ever, so A will always just be there. Okay, and we will just have different numbers of X's and E's. We're going to see that this is going to help us to classify the shapes of these molecules. And so we're going to be able to have a big old chart that will tell us everything we need to know. So if we can classify a molecule according to these letters, then we can identify its shape, and that will help talk about its properties later on. Okay? Cool. Let's see, any others that we have? Okay, how about this one? Let's do... Okay, how about this molecule? Okay, not SO3 2-, not sulfite, but sulfur trioxide. If we do its Lewis structure... You know what, let's actually do this because this will be a good one for you guys to do. Well, it should have 24 electrons, right? If we go ahead and put in... I'm just going to put them as lines right now. Actually, I shouldn't do that. I'll be consistent. Dots. In they go. We have used 6. Therefore, have 18 left. Give 6 to each oxygen. Alrighty, what happens here, guys? You are correct, Shelby, but I was looking for what Marissa was going to say. Both of you are correct. So, we are going to have a double bond, but which one are we going to take it from? Are we going to do the oxygen on the left, the oxygen on the bottom, the oxygen on the right? Okay, we can do it from the bottom one. Totally no problem there. Oops. Yes, go away. Oh my gosh. If we do that, this is what we get, which is absolutely a correct Lewis structure. And Shelby is absolutely correct in identifying this as an AX3 classified structure. Kaz, calm down. Alrighty. However, we could have taken that pair of electrons from the right oxygen also. We could have done that. Now I get to draw 1,000 lone pairs. Or we could have done it from the left. Does not matter. Alrighty. All of these are identical to each other. Okay, we've just moved our double bond around. Okay, it can be any of these. So it does not matter which one we put as our double bond, it could be any of them. Okay? This phenomenon is called resonance. And that means there are multiple correct Lewis structures. So these three structures that we have, this one, and this one, they're all correct. It just depends which one you take that extra lone pair from to make that double bond. And we would call these resonance forms. Okay, the multiple structure ones are called resonance forms. All right, so in this case, sulfur trioxide has 3 resonance forms. Okay, and all 3 of them follow this AX3 pattern. All right, is that okay so far? Cool. Alrighty. This, by the way, you will, on your lab tomorrow, if you're doing exercise D, you will see some of these that have resonance forms. So I wanted to make sure that you guys were aware of that before you went into lab tomorrow. Though I have no idea what you guys are going to actually do, so who knows. Cool. Okay, so does anybody have any questions on identifying this as AX3 or on what resonance means? Okay, so Elsa, how many central atoms do we have in any of these structures? Let's just do this bottom left one because it's the... Yeah, so we have 1 central atom. And how many outer atoms do we have that are bound to that? Yeah. And do we have any lone pairs on sulfur? Nope. So that's it. AX3. So even though there's one that's double bonded, it doesn't matter. We look at the number of atoms. Okay, we're not counting how many bonds, just how many atoms. Okay, cool. So, if we look back to carbon dioxide, what's its classification going to be? AX2. Absolutely. Alrighty. So, next thing we're going to work on if you add up your X's and E's on a particular structure category, that equals the number of electron domains. So, if we had something that was this, how many electron domains does this category have? Yeah, it's got 3 electron domains. How about this one? Yes, of course. Is it Melissa? I agree with Shelby. So remember that if we don't write any number, it means 1 next to it. Okay, cool. Good. No problem. All right, this is important because the number of electron domains this tells us what is called the electron geometry. Alrighty, so let's make a little table here. And it's electron geometry. Now that's nice. You guys thought you signed up for counting or chemistry, but you're also doing counting class and sig fig class and math class. It's all here. Alrighty, pop quiz for you guys. If you had two things that are both attached to one thing in the middle, for example, I have a body with two arms on it. Let me see how the best way to get in here. How could I arrange these arms around myself so that they're as far apart from each other as possible? How am I going to do that? Electron domains do not want to be near each other. Okay, so we're going to figure out how we're going to do it exactly. So if I put my arms straight out like this, I'm T-posing on you guys. If I do that, these arms are going to be as far apart as possible. Okay? What's the bond angle in between these? Like from here to here. What's the angle? 0. Aha, 180. Yeah. 0 would be like this, where they're right on top of each other. But 180 is where they're full apart. Okay, so... we're going to see that this is going to be called linear. Okay, so you can make a line from this arm to the other arm. It just goes straight across. And that's a 180-degree angle. Alrighty, if we have 3 electron domains, let's see, now I have a foot as well. Okay, that's not going to work. Okay, how about my torso? Okay, so I have a torso and 2 arms. What's the best way so that these 3 things are as far from each other as possible? If I just do this straight out again, yeah, I've got 180 degrees between the arms, but my torso now only has 90 degrees in between my arms. So we want to make them as far apart as possible, and I'm telling you there is another way that we can do this. Yeah, I like that idea. So if I go like this, sorry, my camera totally pointed crappily. But yeah. We want to kind of make this kind of Y shape. So I will shrink myself down also so you can see we've got the 2 things kind of up and then 1 thing down. That's a 120-degree angle. That's absolutely right. And we are going to call this trigonal planar. Okay, and if I just kind of draw something... Oh, come on. That's 120 degrees. And that one is 180. All right, advanced time. I now have a head as well. I've got 4 domains now. Ha. Okay, hold on. Robert's got a question. Indeed. So, you're kind of saying 90 degrees between all of them. A square, yes? However, there is a better way. Now we're going to go from our two-dimensional universe into a three-dimensional universe. So, let's see, how can I do this? This is quite funny. 180, huh? That'd be nice, but we still have to consider the angle between this arm and my torso, or this arm and my head. And so what we're going to do is we're going to bring some of these out, and my head is actually going to go backwards. What this looks like, yeah. We're going to have our middle thing. We're going to have one of them that comes out at you, and one of them that goes into the board. So, just visually, this wedge thing means coming out. So that is coming out of the tablet, I guess, in this case. Basically like pointing out. Coming out of it, three-dimensional. And this thing is called the dash, and that means going in. So that is going, like, backwards. So, let me just, like, move this a little bit. Oops. And I dropped it. Okay, there. Okay, so consider that I basically have something like this, and then the other two are like this. So, again, this. So you see these two, and then this. So therefore, all four things, 1, 2, 3, 4. All right, so this is now yoga class. So everybody go up and start doing your, no, we don't have to do that. Okay, cool. So we're going to call this shape tetrahedral. Oh, goodness gracious. Oh, I just realized all this has been recorded, hasn't it? Oh, God. Oh, well. Alrighty, and so it's not going to be 90 degrees, but it is a magic number called 10. Not called, I guess its value is 109.5 degrees. Alright, so this one is special. Let me just see if I can't find a, just in case, I'm going to see if I can find a nice, let's see. Okay, here we go. Cool. Okay, here we go. Boom, look at this. No, that's not what I want. Oh, I see. Yes, we'd be learning that stuff. Okay, let's see. Where did I just save this crap to? That's the real question. Okay, here we go. Aha! Okay, so that's what it looks like. So in this case, it's spinning around, but that's the idea. So we have kind of one straight up, and we've got three others kind of in a triangle, but they're pointing downwards a little bit. So it's not exactly 90 degrees, it's a little bit bigger. I did look like that, didn't I? So there we go. That's what that thing is going to look like. Okay, so the angle is actually 109.5 between those. No, I'm not going to spin. It's too hot in here to spin. So, cool. Okay. Cool. So, do we have questions on... Kaz, calm down. Calvin, go up there. Go up the couch. Go. You can watch the video so you can see me doing this crap again. No, that was Kaz. Kaz does not like the puppy. This puppy has too much energy, so dog life. Cool. Any questions on these? So we're only going to have either 2, 3, or 4 electron domains. Okay? Creature is the puppy? Yeah, you wish. No. Here, I'll bring him up. Come up here. Kaladin, come up here. Up. Yes. Give Daddy a hug, huh? Oh. The licks do not stop. Oh god. Dying. Oh no. Okay, off, mister. Go play. Oh god. Okay, yeah. So, chemistry, right. So, what were we talking about? Right. Electron domains. So, can you guys hear the squeaking out of curiosity? Oh, good. Okay, well, he's now rolling around on the floor with his toys, so... Oh, well. Okay, so... we now have... another one called molecular geometry. Where we pretend the lone pairs don't exist. And so what we're going to do is we're going to then look at what remains. All right, so if we were to draw ammonia, here, let me draw it a little bit better. I'm going to draw ammonia kind of with those bond angles. So I've got my lone pair going straight up. I've got kind of one of those hydrogens down. This hydrogen is coming a little bit at you. And this hydrogen in the back is in the back. And so if we scroll up to that spinning delightfulness, here it is, our spinning molecule. If we pretend that that top part wasn't there, but keep the rest exactly as it was, that is to say, if I were to make this a little bit more pronounced, what's kind of the leftovers? If we pretend that this part does not exist, what is the rest of the molecule resembling? If we look back at our spinning doom tetrahedron here, if we pretend the top one doesn't exist, we still have that central atom and 3 atoms kind of a little bit down, right? And so that kind of looks like a pyramid. Yeah, that's kind of what we're going for here. Yeah, pyramid. Cool. We're going to call this... I guess I have to make another table, huh? I'll just write it, and we'll make a table later. Trigonal Pyramidal. So it's a triangular pyramid. Okay, so 3 kind of bottom thingies on that. Okay, you can just write trigonal pyramid, that'd be okay, but typically people write pyramidal, because why not? Alrighty. How about hydroxy acid? So again, we're going to pretend these lone pairs don't exist. What's going to be left over in between that? Is that linear? Is this linear but at an angle? Okay, I kind of. So pretend it's like this, Shelby. So just my arms. So is that quite linear? Not quite, right. So we still kind of have that 109.5 degrees. It's a sad one, yeah. We're actually going to call this shape bent. It is bent out of shape. Yeah, you're funny. Wow, bringing in WoW lingo too, huh? Nerd. Okay, so we have more shapes now. So let's go ahead and assemble our table. Alrighty, by the way, ammonia was what type of molecule again if we were to classify it? As in A's and X's and E's and stuff, what would ammonia be? Neither of you is quite correct. None of you know. Aha! That's right, Samuel. Right. We have a lone pair on there. Don't forget about the lone pair. All right, and if we have water, what was its classification again? AX2... What did I cross? Yeah, E2. So we see that both of these guys actually have tetrahedral electron geometry. I just threw out a bunch of fun words at you. Remember that X's and E's, when you add them up, if it equals to 4, that's tetrahedral in terms of electron geometry. How exciting. We're going to make this big-ass table now. I know, so many new words. But look, Trigonal Pyramidal and Bent are the only new ones for you guys. So, let's go through a bunch of examples. Yeah. So, let me make our table first, and then we'll go over the classification. Okay, what does X and E equal for all of these if we add up X's and E's together? They all add up to 4, right? So that means that this guy is going to be, well, not trahedral. Tetrahedral. All of these will be tetrahedral. Because they all have 4 electron domains. Tetrahedral is the spinning shape that we saw up there. We just looked at something that was AX3E, and we saw that that looks like a pyramid. Trigonal Pyramidal. Okay, and then this one we saw was bent, our water. However, we have not yet looked at something that's AX4 or AXE3. So let's do an example of those, and then we'll come back to this table. Alrighty, here's one for you guys that we've already done. Here's the Lewis structure. What's its electron geometry going to be? Electronically, yes, Robert, they're all tetrahedral. But molecular ones can be different. Yeah, it's AX4. Yeah, sorry. Of course, it's AX4. And so, we have 4 electron domains. Do we have any lone pairs on this? No, we don't, right. So we're going to see that if we were to draw this like with the, kind of 3D way, this is also a tetrahedron. Nothing is changed because there are no lone pairs. So all of these are still 109.5 degrees. So our shape molecularly is still tetrahedral. Exciting, isn't it? So its electron geometry and molecular geometry are the same because there are no lone pairs. When we put in lone pairs, that's when our molecular geometry can be different. All right. Let's take a look at another one. Iodine monochloride. Lewis structure, I'll just do it for you. If we look at iodine, how many... It's got one central atom, of course. Looking at iodine, how many outer atoms do we have? Six outer atoms? I like that better, yes. Whoops. Yes, just one. We have the chlorine. And how many lone pairs do we have? Yes, 3. So this will be an example of an AXE3. If we pretend, again, our lone pairs are not here, what's left? I mean, yes, but I mean just shape-wise. We only have 2 things left, right? What's any shape between 2 points? Is it a triangle? It's linear, yeah. It's not a rhombus or anything fun. It's just linear. Yeah. Fun is fun. Alrighty. So for all formulas that have 4 electron domains, here is the chart we're going to use. The electron geometry will, for all of them, be tetrahedral, but the molecular geometry will be different, depending. So if you can classify a molecule as belonging to one of these 4 categories, you will be able to come up with its electron geometry and its molecular geometry. And we're going to see that like this, the point of doing all this is going to explain properties about these things. Okay? So far, so good? This will unfortunately carry a bit of memorization, but I think this is a relatively easy way for you guys to remember these things. All right. Let's go back to our Y-shaped molecule, the triangles. We're going to have AXE2. Yeah. All of these, the electron geometry, do you remember what these would be called? The Y-shaped ones? Trigonal planar, yeah. Very good. Remember, they kind of look like triangles. We saw, for example, this molecule, right? What classification would this get? How many central atoms? Outer atoms? Lone pairs on sulfur? None. Yes, very good. So, this is also going to be trigonal planar. Remember, if you do not have planar, oh god, that's hideous. Planar. Cool. Alright, remember, if you don't have lone pairs, your electron and molecular geometries are the same. So, I'm just going to, for brevity's sake, draw something like this. What did we say about this shape? What does this look like from before? Sad indeed, and remember we call that one bent out of shape, right? So this one that's AX2E, that's going to be bent. Why am I writing it here? I don't know. That's nice. And then if we somehow had something that was like this, what's its shape going to be? Linear again. Yeah. So you see we're not learning really any new words except for trigonal planar on this one. Cool. I just want to quickly go over the last one, which is AX2, AXE. Not sure if that exists, but these would just be both linear. All right, for example, that, linear. That's an AX2. All right. So the ones with 2 electron domains are no problem. If you have either of those, linear is your answer. Alrighty. Let's do, we have 7 minutes. Let's see if we can't do, goodness gracious. Let's do 2 problems, okay? And then we'll continue doing this next time, but you will be doing the same thing in lab on tomorrow. Let's do that one. I want you to come up with the Lewis structure as well as the electron geometry and the molecular geometry. Okay? It'll be nice and exciting. And let's do that one. Let's see if I have a good... random picture from the interwebs, but there you go. That's kind of what Trigonal Pyramidal looks like, for example. Just so you guys can see more visually better than I can draw. Yes. Even better. Oh, I know, you're not going to have like a real lab for a couple of weeks. Yeah. So interestingly, so when I emailed him about the experiment 4, telling him that we're doing like May 17th or something like that, he was like, "You guys are so behind," and I'm like, "We're not," and that one's not supposed to be done for another month. So I told him you guys would be ready for exercise D next week, but I don't know what he's doing. So if you're doing B, even better. You'll have more practice naming. So no. In fact, this should be easier for you then. Naming, definitely a very important skill, so I would be happy for you guys to do more practice. So as long as he believes you guys are on naming still, then that's fine. That's okay. Okay. So, oh, you guys gotta see this. He's all up on the bed. And look, little Kaz here taking up his own bigger bed. But yeah, he's all curled up on this thing. Uh-oh. It's awakened. Of course. Yeah, that's how they work. Chihuahuas always take the big beds for themselves, right? That's just what they do. So, okay. Anyways. Nice. So it's electronically and then molecularly. It's trigonal planar. Very nice. Wow. Very nice. So that is tetrahedral. And that is bent. Very good. So again, electronically tetrahedral, but molecularly bent. Let me see if I have a good picture of bent for you guys. I'm seeing all these. Oh, because I searched Trigonal Pyramidal. No. Okay. Ta-da! Here it comes. Boom. There's bent for you. Sad. Alrighty. So it is roughly 5:30. So do you guys have any last questions? We're going to continue this on oh God, what day is it? Wednesday. And we will do a lot more practice with this, of course, and then we'll start talking about polarity. Okay? Alrighty, take care, guys. I will eventually grade your homework, by the way, but it's okay, you guys already turned it in, so nothing due, just so you know. Alrighty, see you next time.